Over here. So these are up conversion again, and you can take a CW laser, continuous wave, low power laser, like handheld laser, which is in invisible range, and I heard that by 2 photon climbing to emit in the infrared, or you can take even more deeper IR and convert that into green by 3 or 4 photon process, or you can convert in the UV. Generally, with any ion like thulium, you have many up conversion by 2 photon at 800, by over here looking at this, इसको जरा ऊपर उठा दे, ये नीचे वाला नहीं आ रहा है, projection, just a little bit. Take. Yeah, that's good. Thanks. So, in the same thulium ion can climb up further, and by 3 photon can give you light in the blue. For 4 or 5 photon, it can give you in the UV. You have many up conversion wavelengths, and maybe for some application, you want to have maximum emission only by 2 photon, 800. And other application, you might want to have more light into blue. Blue light may be absorbed more strongly to do what you want to do there. So how do you actually enhance more emission over here for that application, or more emission over here? And this is where you need to understand the physics. And so there is a lot of what we call nanoscale control of how the excited energy, you can make it flow in different channels and emit. So that depends, and again, since most of you, there is no physicist here, is there? Okay, so we will just talk about, in general, that depends on, firstly, what kind of crystal phase you may have of the nanoparticle. So the same nanomaterial can exist in more than one crystalline phase. And so you want to choose the right phase that gives you maximum emission, maybe emission in certain channel. Then you want to have a lattice of that crystal that does certain kind of energy transfer process. Then you want to control the surface of, because surface generally can also deactivate. So a lot of energy can be lost from the surface in there. So you want to make sure that these things are, by understanding the physics, and I wrote in a review called Account of Chemical Research, you can enhance maximum emission or emission through selective channel. Okay? So here gives an example that if you take the erbium in the same sodium yttrium fluoride, ytterbium, so these two are dopant. When I write it this way, that crystalline lattice or medium is the sodium yttrium fluoride, ytterbium is doped here 20%, and erbium is doped in this 2%. So that's the designation. And and they are 20 nanometer, but they can be in 2 different phases, crystalline phases, cubic or hexagonal. The cubic, being very symmetric, the up conversion is very small. But you go to hexagonal, the up conversion at many wavelengths is very strong. So you want to choose hexagonal phase, you want to make sure. And how do you choose the phase? In the X-ray. So you can do X-ray powder diffraction, that's the simplest, and look at the pattern of the powder diffraction and see which phase it is to. Okay. a lot of times you want to make not only a core but a shell, okay? And the shell can be inert. That means it can only protect the surface from deactivation. So that we call inert shell. Or the shell can do certain thing also. So the core can upconvert. It has one kind of ion, and the shell has another kind of ion that can upconvert to another wavelength. Okay? And then you can make multiple shells. So one case is where these shells are roughly the same crystalline type of structure as the core. That's called epitaxial cell. The other one is non-epitaxial, and the shell material is very different. Like your core may be fluoride crystalline lattice, and the shell may be silica. Very different. So that we call non-epitaxial. Or you can have not shell, but you can have decorated organic antenna. So it's organic molecules attached to the surface. Okay? So you can have that kind of decoration for the function. So how do you make these? Epitaxial one is easy to make. You can make a core first, and then you can either do exchange. Suppose the shell you want to make is instead of one ion, it is another ion. So for example, instead of yttrium, you want to have calcium, you can exchange the cation. You can do chemistry to exchange it and you form a shell. Okay? Or you can add precursor under different condition. This core acts as a seed, template, and the cell starts growing. Okay? So it's called seed-mediated growth. Or sometimes you can have a lot of nanoparticles trapped in there, and they combine together, called osmolar ripening. So they decorate around, and osmolar ripening, they can form a shell. So these are three methods, and again you can read it in my review article that I wrote in Chemical Review. Gives you detail of making it. So it's a very simple chemistry, okay, not very complicated. And what do we use core shell for? The shell can do, it can introduce new functionality, or it can protect the surface and prevent quenching. It can absorb light more and get into there. So, and then if you use metallic, then you can have plasma resonance. You can do energy transfer control between two layers. So there are many things you can do with core shell structure. It's a very useful structure. So this gives you some examples of how you characterize them. So very often you can actually do TEM, transmission electron microscope, and you can see core and shell structure. So because in this case it is sodium gadolinium fluoride doped with sodium, and then your shell is sodium yttrium fluoride doped with others. So you can actually distinguish and look at whether you actually have formed core shell or you haven't, is only core. Or they have two different crystals. One is for core material, and one you thought is shell material. Rather than forming core shell, they want separate two nanoparticles. You don't want to make that, right? So anyway, this gives you an example that how by putting the shell over here, so over here the core is this, and then you form a shell on that of just calcium fluoride is on the top shell. Okay, so in this core shell structure, you minimize surface deactivation, and then if there is no rapid relaxation, then what will happen is that they can climb up more ladders. They don't relax very fast, dump energy, because surface is protected. So they can climb by 1 photon here, 2 photon, 3 photon, 4 photon, and you can have actually 4 photon induced blue emission. or UV emission in this. And we showed that if you put this kind of shell, then this up conversion by 4 photon into UV or blue is enhanced like hundreds of times, very strongly enhanced, because the surface is protected. Okay, so the core shell structure is very important, especially when you want to climb up very high, go by 4 photon or something. Okay. Another thing we showed that very often, see, if you take rare earth ions, this is the emitter thulium. Ytterbium is what we call it sensitizer. So light is generally absorbed into ytterbium 980, and that transfers the thulium to climb up and emit from different levels. Okay, but this absorption by ytterbium or thulium again is F to F, and that transition is not very strong. Organic dyes are very strong absorbers. So what we showed, that if you take actually a core which is of this, and then you have a shell which involves neodymium over here, and then on the top you have organic dyes attached. Okay, this is in this case was indocyanine dyes that can absorb very strongly in the near IR, because the dyes are very strong absorber. That's why they could be very strongly colored, right? So they can transfer energy in many steps to enhance the emission over here. And we showed that this up-converted emission is so much enhanced. Without this dye, if you look at in this scale, the emission is very weak emission, this up-conversion at 800 in thulium. But when you do this way, is 100 times enhanced. Okay, very strong, that you can even use a low power lamp. You don't even need a laser. A lamp at 980, in this case is 800 nanometers, and it can be up converted very strongly. Okay, so we show that this energy transfer process, so these dyes act like antenna. They're antenna, they absorb light and they funnel the energy into the core where you can emit light. Okay, so then this is an example of core shell structure, that each region up converts to certain region. So like in the core we have erbium, and it takes light at 1500 nanometer, converts that into green or red color, okay, or IR. You can take thulium, which is in this layer, and the thulium takes light at 980 or 800 and converts that into 800 nanometer or in blue. And then another layer is holmium that up converts over here. So you can map out up conversion or energy transfer many different wavelengths, each region doing certain things. Okay, so this is an example of that. Now again, as I said, in nano formulation, the excited state light, excited state can emit strongly if you want imaging. You can do photochemistry, you can do heat generation by looking at nanoscale manipulation. Okay, so let's just skip this. So let's come to characterization of nanoparticles. How do we characterize them? What do we do with them? So here, first we want to do physical characterization. So you have made the material, right? And you want to look at their size. So how do we determine size? Size you can do firstly with XRD, X-ray diffraction, pattern, and its width can give you some information on size. Then you can also do TEM, transmission electron microscope. With that you can actually see the size and the shape together. Okay, or you can do dynamic light scattering of this first one, and you can get information on the size. That's called hydrodynamic radius. Effective radius of nanoparticle dispersed as a colloid. That's by dynamic light spectrum. Or you can do AFM of the sample, dried sample. So these are the ones: size, shape again you can get by transmission electron microscope or atomic force microscope. Then you want to know whether it's crystalline or amorphous, the nanoparticle. And if it is crystalline, what kind of crystal phase it has. Like I showed to you in case of erbium, that it could be hexagonal or cubic. So you want to determine, and for that you do X-ray diffraction or high resolution transmission electron microscope. Okay? Then you want to see surface charge and whether they are uniform nanoparticles or they have a large size variation. It's called polydispersity. And for that, you can do dynamic light scattering or transmission electron microscope. And you can look at different nanoparticles in there with TEM. Surface charge again with dynamic light scattering. Now if they aggregate, so you take firstly TEM, and you can see the nanoparticles, they are small. And then you go in dynamic light scattering, and it all of a sudden you see the sizes are not 50 nanometers that I saw in transmission electron microscope, but it appears like 500 nanometers. What does that mean? That means those in colloidal dispersion, these nanoparticles have aggregated. They have made a bigger size nanoparticle, which you really don't want to use. Okay? So now you have to use methods to break down that aggregation, and they're more dispersed. So this is the first step you want to do, is when you make the material, you have done elemental analysis to confirm that those atoms are there, that is the right kind of material you have. Then you want to do the size, shape, whether they are crystalline, and what is the charge on the surface. Are they monodispersed? If not, then you want to improve the condition so that they can all be very similar, and then whether they're aggregated in dispersion. You want to make sure all these. So let's look at some examples of imaging and diagnostic, and then after that, my goal is that we can run through imaging faster, and then we will get on sensing, and we will get to therapy, because a lot of you are interested in how do we apply to therapy. Okay? So imaging, again, as I said, you can do many different kind of imaging. A nanoparticle allows you to do that. An optical probe, either you can use organic dye filled in a nanoparticle, you can use quantum dots, that up-converting nanoparticles I talked about. You can also use metallic nanoparticles because they absorb strongly, and they also scatter light strongly. So if you use a scattering, it's called, then you can do dark field imaging, contrast versus the background, because the light is scattered, so those things appear dark, over there. Okay, so one of the dyes we use, because let's go back to that, and this is interesting for those of you who are synthetic chemists or organic chemists. So let's look at dye containing nanoparticles. So how do we do that? Well, you can either take, when you make nanoparticles, you can put a dye in there, and the dye, if it is hydrophobic, it can get inside the hydrophobic part of the nanoparticle. When you are forming, it will include the dye in there. That's called preloading. It means as you are forming, the nanoparticle getting in there. Or the nanoparticle may be mixed with the material, like polymeric material, and they are uniformly distributed, and you have nanoparticle, okay? Or you can have a porous nanoparticle, like silica, mesoporous, and you can post-load it. You can fill dyes in the pores Okay, so there are many ways, and the same principle goes for drugs, how you encapsulate. However, the dyes, most dyes have this property that if you load them in high concentration, because you want to make them brighter and more emissive, their emission is quenched. That's called concentration quenching, or higher concentration. The dyes, when they come together, they decide not to emit but go as a heat. So concentration quenching, you want to avoid that. So what do you do then? Then you want to kind of use a low concentration of dye so that they are not aggregated, they are dispersed. But if you use a low concentration and you want to do 2-photon imaging, which is a weaker process, you don't get enough emission. So there is a problem. So we synthesize dyes which actually works in the opposite way. These kind of dyes, in the middle is a floppy ring, like naphthalene, anthracene, or tetracene, big fused rings that they're rattling around like this. So when you use a monomer, like without aggregation, like this, these rings are rattling very fast. So when you excite them, the energy is dissipated by this rattling. Not much emission coming out. But when you aggregate in high concentrations, they pack together. And how do they pack? These rings have pi electron cloud. And there is a pi-pi interaction between different rings. And so they stack together like this, and now there isn't much room for them to rattle big. They can rattle a little bit towards null angle. We calculated by quantum simulation that in this case the rattling angle can be 74 degrees, but in this case is only 38. Okay, limited. Okay? So in this case they are much more emissive. So if you use high concentration of this, or even a pure dye nanoparticle, it will be much more strongly emissive. Look at this here. This is a monomer dispersion. Individual molecules dispersed separately. Very weak emission. When they aggregate, very strong emission. Okay? So these are much more suitable for imaging. You can make nanoparticles of the dye themselves, or you can attach these to a polymer, either a main chain or hang on the side chain, and they will be very strongly emissive even on high concentration. Higher the better. So we use these, we call these aggregation enhanced dyes. Okay? So one of the ways we have done, look here, these are some of the molecules where we also show aggregation enhanced, and we can either use a small molecule or we can put them in polymer structure. And one of the methods we have utilized, one is to make through this chemistry, nanoparticles, or dope them, but if they are polymers, you can also focus laser beams very tightly, short pulse, and ablate it, fragment the polymer to come out in a solvent, and you can make nano suspensions of these materials. So this is called laser ablation technique to make nanoparticles. You use a solid target, focus the short pulse, and it ablates. But you want to keep on rotating this substrate material so that the same spot is not always hit, because it might burn the polymer in a long course. So you want to do this. So this is one method of preparing. Anyway, we showed that indeed you can do make nanoparticles, you can do energy transfer between two dyes in nano formulation, and very effectively image. We can also coat them in surfaces and get them in cells, and you can do imaging. Okay. Then the other thing we did is for head and neck tumor is that we want to combine two modalities of imaging. Okay. And this is example. One of you asked whether we could do phosphorescence for imaging. This is where we had a dye that phosphoresces and included it with gadolinium. Okay, so the gadolinium provides MRI contrast, and this organic dye that phosphoresces provides optical contrast. So we can do double modality imaging. The other one is quantum dots or rods. Rods is not spherical like this, but long way. And you can again you can size tune them firstly. So cadmium selenide, you can cover a certain range. Then you go to cadmium telluride, it covers this range with the size of indium phosphide. And so by using a combination of either size or composition, you can cover all the way from here to IR. Okay, and image them. Now, these emissions compared to organic dyes are very narrow. They are like 10 nanometers wide. So you can use different particles and collect emission in different channels, label them. That's what is called multiplex imaging. Okay. Then we found that again, if you put a shell over this, then it's much more emissive because it protects the surface from deactivation. So that's why if we use cadmium selenide, let's say, we will put a shell of zinc selenide. Zinc selenide is wider band gap semiconductor, so whatever light is emitted here will not be absorbed by the shell. It comes out. Okay? And the cell's function is to protect it. Then we put a layer of organic like lysine, which is amino acid, to make it dispersible in water. Okay. And then on the surface, we put these antibodies, remember, with a lock that grabs onto antigen on the surface to attach and get in there. And then in addition to that, you put this pegylation group, which is polyethylene glycol, very often abbreviated as PEG. You attach that because that one enhances the circulation of nanoparticle in blood so that it has more time to find where it's supposed to be by this targeting group. So this is the kind of nano formulation you use for imaging if you want to do that. But the same strategy you can use for drug delivery if over here in these regions you can include drug, or on the surface you can attach the drug. Okay? So this is a pancreatic cancer cell line where we use a quantum rods, again a longer one which has emission little shifted towards red, and the quantum rods are sometimes much brighter than the spherical nanoparticles. So we use that. Here is orange emitting quantum dot with one kind of antibody, and red emitting quantum dot with another kind of antibody attached, so that this recognizes one kind of antigen on the cell, this recognizes another, and it turns out the pancreatic cancer has both kinds of antigens. So when they are both expressed and you see effect of both attaching to both there on the cell, you know that that cell is really pancreatic cancer. So there are two signatures we are identifying to verify that indeed it is pancreatic cancer, not something else. Okay. So let's look at in vivo now studies. So what do we do in vivo delivery? In vivo delivery, first we have to choose the delivery route. How do we get nanoparticle inside the body? And there are many ways. A simplest way could be through oral. You take it as a pill, some formulation, or you have a nanoparticle suspension, you drink it. It gets into your, through your channel in there, and there in the stomach, it can be absorbed into the blood stream. And so it passes from there inside your system, and then it can circulate. So that's oral delivery. What are the other ways you can deliver? Systemic, we talked about. We inject in the blood, circulates around. You can topically inject, so you have a tumor and you look through it, or some skin tumor, you can see where it is. You inject right in there, okay? And you can also, in bladder and other cases, also through endoscopically, you can deliver right to the point. Okay, so that's called topical or local delivery, right? What other ones? Through the skin. You can have nanoparticles and patches put on here, the patch, and it gets absorbed in the skin, and through the pores it can get in there, right? So that's another, that's called transdermal delivery. Is there any other kind? Through nasal spray. Yeah, I was going to say. So you can spray in the nose and it goes through that channel cavity inside, right? So there are many ways of delivering. I need to choose for a given disease what is the best way of delivering it, okay? And so you need to decide that. Then what you want to do is a very important part is crossing the biological barrier. These nanoparticles have to cross our body's defense line to get inside our bloodstream. And in each case there is a specific problem. You're talking about skin, there is a skin barrier. When you do the oral, there is a mucosal barrier, or mucus in the mouth try to protect, from getting inside. You're looking at getting into the brain, nervous system, there is a blood-brain barrier. The nanoparticles of foreign object have to cross. So you need to determine how we can make nanoparticles that can penetrate through this, So we will see later that what we do is in our laboratory, we make phantom models. So these are kind of replicas of what a barrier would look like or made of. And then we put nanoparticle suspension on one side, which is tagged with fluorescence. And then you say whether it can cross, and I can see fluorescence up here, the upper channel. And if we see more coming, then we know the nanoparticle is penetrating through the barrier going. So we do a lot of this investigation, particularly in the blood-brain barrier. We simulate the blood-brain barrier. That's what we call phantom model. And then we can see, first step is whether these tagged nanoparticles that are emitter, they are crossing, and we can detect by fluorescence on the top, right? And then we can monitor, as we showed to you, the injecting in the tail vein, monitoring emission in course of time, how the nanoparticle migrates through the body to get to the target, which is the tumor. So that's what is called biodistribution. And that is then targeted delivery. Eventually, the target is reached because there is a targeting group looking for that site, right, where there has a stronger affinity. And then we want to have therapy. We can image and look at how tumor is spread, and then we can treat, and then you can image again to see how the tumor is shrinking, whether effect is working or not. So that's C, T, and C. And theranostic again is therapy plus diagnostic together. And then eventually we want to make sure that those nanoparticles are excreted. So this is again, we already talked about earlier. These are very important things that you need to evaluate for your nanoparticles and modify it. How? Chemical makeup, size, charge, surface coating, all these manipulate so that you can get quickly through the delivery route. It crosses biological barrier, it has favorable biodistribution to reach the target, then it does the effect and is excreted. Okay? And then again, these are the barriers we already talked about, and you can read through this chapter. Now, targeting. What are the things we can do targeting? How do we target a given site? So the first one is passive targeting. A passive targeting means you do nothing special to the nanoparticle, and they still kind of circulate and find the right spot to get in there. And how does that work? Well, it turns out that in case of cancer, the vasculature, is very different, near the cancer site, tumor tissues than normal. Okay, because it has to make more channels, so on, for bloods to feed, because it's very rapidly multiplying and growing. Okay, so what happens is a certain size nanoparticles, if they're bigger size, they get into those and they are held in there because the vasculature is increased. So it goes in there, it's like a sponge. It soaks in the nanoparticle and it stays there. Okay. So if you want to use passive targeting, then your nanoparticle cannot be very small, because very small they can get in and out around that. You want to have a bigger size, 50 to 100 nanometers, they get in there, they're soaked in there, and they stay. It's called passive targeting. And this is also known as EPR effect, enhanced permutation and retention, permeation and retention, EPR effect. So this passive targeting work by EPR effect. Look, EPR is also used for electron paramagnetic resonance. Well, that's different. Here in biology, EPR enhance permeation and retention, okay, nanoparticle. So that's one way. You will also see the photodynamic therapy. These porphyrin sensitizers are used to absorb light and kill cancer. These ones also do auto-targeting. They themselves like the cancer cells. So they go there, they stay there for much longer than normal cells. So that is, you're not doing any active, but it's doing it. Second one is field directed. So suppose you put in the nanoparticle some magnetic nanobead together. And now you can take a magnet and drag it, a nanoparticle, to the tumor. That's called magnetophoretic control of nanoparticles. So people have done that to enhance also the targeting. More and more nanoparticles to drag it to the tumor. Okay? And then the other one is intrinsic targeting, as I said, a photodynamic therapy. These porphyrins, they themselves want to drive and find it. And the last one is what is called receptor-mediated active targeting. That means you put active groups like antibody or something on the surface to target, okay, to look for this thing. So this gives you example of how the capillaries are in the tumor and how it gets sponged, acts as a sponge. This you already saw example of. This is example of, again, regulated nanomycel thing to target. So you can see it's targeted, more nanoparticle getting in targeted. Mostly it is in liver. Okay. Again, we talked about in case of light, if you're using light to get in there to do anything with a nanoparticle, you want to make sure that you are in the wavelengths of either first window, second window, third window to get deep inside. This we already saw. Upconversion. So this upconversion, how do we use in biology? So we can do one upconversion when you get from IR to IR, like 980 nanometer to 800 nanometer. That's much more useful because you can penetrate deep through tissue, no photo damage, and there is less absorption and scattering of those wavelengths, so they are much more suitable for imaging. But when you want to activate a therapy, either killing bacteria or can initiate some photochemical reaction locally, or you can activate a drug, most likely you will look a shorter wavelength even. You want to get more to blue and UV. So this upconversion blue and UV is more for therapy. IR upconversion is more for imaging. Okay? So here is an example of upconversion where we excite those upconversion nanoparticle. In this case is thulium doped in a fluoride lattice, and if you excite at 980 nanometer, this light can go deep inside the tissue. Okay? Then the emitted light is at 800, higher energy, but this still is in the window and it can come out. So you can get light deep into the tissue and you can come out. So we showed that we can very effectively image cells, but that's not a big deal. Then we also showed that we can use these nanoparticles for imaging in vivo, in an animal. This is a mouse. So again, nanoparticle injected, it goes and finds the tumor, and the tumor lights up. When you excite at 980, emission coming at 800, we can image it, the distribution of tumor. Okay? Size and distribution of it. And these green ones are emission from the hair of the mouse and all those different color. We don't need to worry about it. Okay, so this was, we have used very extensively, but then it actually was not good enough for popular press. They couldn't visualize how deep you are going, how we're imaging. So what we did, again we used, remember that I talked about phantom model of tissue. I showed you chicken breast in that other case. So here there are three pieces of meat, is pork chops that people in America eat. They are generally, a few centimeters thick. So they start with three pork chops. Then they take this nanoparticle suspension, they put at the bottom. And then they excite it by 980 light going this way, and to excite those nanoparticles, emitted light at 800 coming out, and we collect up there. So you're looking at more than 3 centimeters of tissue, and we could still see the light coming out, emission. So that shows very clearly that this wavelength light, this window, you can go really 3-4 centimeters deep into the body tissue to image or to do therapy. So this one received a lot of attention from the public press because that was very clear visual. Wow, you can go through so much layer, light can go and you can image. So this was like a big thing for them. This one was not, because I said, okay, you're imaging, I don't know how deep it goes, what it does, right? So that was, now then we also see, you'll see later on, that we took a human skull, and we showed also that this light can go through the skull, and you can image from under this skull at this wavelength, without making incision or anything, just send light. Okay, so that shows the power of it. Then And another area which is important is combining, and we'll come back to that later. The same nano formulation, combining other kinds of imaging modality. So you have optical imaging, you can also do magnetic resonance imaging by using another nucleus, fluorine compounding compound, or including iron oxide nanoparticle, gadolinium nanoparticle, or manganese containing, Mn2+, they're all good agent for MRI. Or you can do this positron emission tomography, for which you need to have radioactive iodine-124 incorporated. So you have to figure out how you can make organic structure that can grab iodine after you have made all this. And when it grabs, you want to make sure that what it grabs is radioactive iodine-124, so that your nanoparticle is radioactive, and you can do this imaging. So those are some of the imaging techniques you combine with. And these are details. We published a paper where we showed that we can, the same nano formulation can do 6 different kind of imaging. So this is an example of how you can do multimodal imaging in the same nanoparticle. Now this one is, again, as I said, you want to make sure the nanoparticle doesn't stay in the body. Either it is broken up into little pieces and is excreted, or it's small enough that a whole intact nanoparticle can come out. So you can also optically monitor that. You can see that nanoparticles are lesser, for example, in liver. And then in course of time, 72 hours, you see that that emission has faded away. So it's excreted from that organ, is gone. And similarly, we can look at the whole animal and see whether any part of the body lights up or not. If it doesn't light up, that means this nanoformulation is gone. So one way is to look at the imaging of the whole animal, and you can do optically. The other one is that you sacrifice the animal and you look at different organs, and in each organ you excite with light and look for is there any emission coming out, is there any nanoparticle here, is there any nanoparticle here. So you can have mice and you can sacrifice some mice one day, another 3 days later you sacrifice another batch of mice. So you can give you time sequence, how long does it take for the nanoparticles to come out. Okay? So that study is very important also, excretion one. And this is again, I showed to you that we make, where is it? Blood-brain barrier. So you can look at the below the barrier and above the barrier, and above the barrier, or here in this case, above the barrier, and you see how the intensity fluorescence is dropping as the nanoparticles cross to below the barrier. And you can see below the barrier the emission is coming out. So we use these kinds of models in our lab to see what kind of nanoformulation, what do we need to do, what will be the size, what will be the charge, what will be the surface that will allow more rapid and maximum penetration through this. Okay? So through these phantom models. Okay, you can also do sensing using nanoparticles, and this part I'm going to go through very fast because I want to move to the therapy area. Okay, so in the imaging thing and what we talked about, any question, anything you have? Yes? Excuse me?
After the degradation of nanoparticle in the body, will it emit the fluorescence?
Well, it depends. It depends on whether you have whatever is emitting is intact. If it is not emitting, then if it is not intact, then it may not emit. For example, if you have a nanoparticle breaks down into ions and so on, it may not emit, right? Or if the nanoparticle is excreted totally, it will not emit, right? And similarly with the dye, if the dye is loaded, nanoparticle breaks down, and if the dye is eliminated from the body, it will not emit.
So if the nanoparticle is coated with dye and degradation takes place, nanoparticle picks out of the body and dye remains there. Few
It's
amount of dye remains there at that place.
no. What happens is more likely the dyes will come out unless there is some kind of specific chemical binding, right? Otherwise, dyes when come out of nanoparticle, they are molecularly dispersed. They are much more easier to get out of the body. Small molecules, they are not size nanoparticles are kind of held in there because they're physically bigger. So that doesn't happen, that the dye will stay, a nanoparticle comes out. It can happen in a different way, not in terms of elimination, but you need to make sure when you load the nanoparticle with dye, suppose you're loading it, you want to make sure that when you put in the body, before you image and all those, the dye hasn't leached out and gone every place. So leaching out problem of the nanoparticle you have to protect, because you want to have the dyes along with the nanoparticle go to the target where you can image it. So you need to make sure that those dyes are held tightly inside the nanoparticle. They are not just loosely, that when you put in the body something, they are leaching out, coming out. Okay? All right. So let's do any other question? No? Okay. So sensing, we already talked about surface plasmon. These use, so more emphasis now is on these nanoparticles. How we can utilize nanoparticles for sensing. इसमें कुछ बैटरी वगैरह लगाना होगा क्योंकि अभी फेड कर रहा है. Okay. Anyway, so these nanoparticles, metallic nanoparticles, they are utilized in many ways for sensing. One of them is, as I said, that they absorb a certain wavelength or scatter, which matches with their plasmon band, plasmon resonance. And these ones, they depend on a number of things. There is a small dependence on the size, very strong dependent on the surrounding medium. And so this goes to you, the different size nanoparticles, they may have slight shift in the case of gold, but primarily they're around green region. Okay? But if you use them in a gold, like core shell structure, so you have core of organically modified silica with a lot of gold nanoparticles, then their plasmon resonance shifts, and the shifts is related to the ratio of core to shell thickness. Okay? So you can tune the wavelength of this optical resonance by varying the core shell structure and ratio. The other one is rod shape. When you have rod shape, the electrons are confined in this direction differently in this direction. So in longitudinal direction, the electrons can move around over a much longer distance, whereas from transverse direction, they are confined only to a cross section, right? So what happens is that in this case, there are two plasmon resonance, one corresponding to the longitude transverse, so the free charge oscillating in this direction, That's called transverse surface plasma resonance. That doesn't change even if you change the size of these nanorods. Basically it stays around green. But this longitudinal surface plasma resonance shifts as you change the axial ratio. Ratio means ratio of length to width. You change, you can tune it. So the tuning of this plasma resonance to suit your purpose can be either by using core shell or by using this kind of anisotropic structure. So there's a lot of interest now in making metallic anisotropic structure. Okay? In nanoparticles you can put dyes that are sensitive to pH for pH sensing, and again you can read this more detail in here. You can use these metallic nanoparticles that the light is coming, interacts with metallic nanoparticles to generate surface plasma resonance, and the near surface plasma resonance, if you have organic molecules, their Raman scattering is significantly enhanced, and that's called surface enhanced Raman effect. Okay, SERS, S-E-R-S. So you can say surface enhanced Raman spectroscopy using that. So it enhances the sensitivity. So very often you may have these nanoparticles sitting next to organic structure whose Raman spectrum you want to enhance, to detect it. Remember I earlier, very second talk I talked about how Raman can be utilized to profile the cell and lipid. So you can do that, or you can enhance fluorescence, or you can use these as a scatterer to draw the contrast with other parts of the cell to image. So they are used in many ways, metallic nanoparticles, and this part I'm going to skip through. You can read this. Oh, yeah. Okay. Yeah, well. Yeah, I'm going to go through. Okay, so I'm going to go now in therapy. Therapy area, we'll talk more about it. So nanotherapy. So here, in looking at therapy, we had to look at the following aspect. What do we want to accomplish by using nanoparticle? One of them is enhanced drug delivery. We're going to have more drug at the local site. So when you administer a drug, let's say orally or in your blood, it's going to be distributed all around, okay, the body. And maybe you hope that it will reach the tumor site, and then you can actually have more effect, right? So what happens, you know that chemotherapy is a very powerful way of treating cancer. But chemotherapy is also a very, very terrible thing, because it really has a lot of side effects, because this chemo agent can be other places too. So side effects are worse sometimes. Some people, they die out of side effects. Okay? So what you want to do is you want to protect those drugs till they reach the target, the disease site, the tumor, and then only you want to release it. So there is very high concentration of that drug at the site where you need it. That's the beauty of nano, that you want to use it for this, using multimodal carrier. You want to release it at the site and increase the concentration. Oh yeah. So the second one is controlled release. So we want to control release, that when it doesn't open up and release the drug till it is at the site, and then it releases there. And hopefully you also want to have a way that maybe you can have sustained time release. So he's kind of over course of time is releasing and acting, okay? So that's another thing. And then you want to monitor its efficacy. Not how do we do normal now if they have a chemotherapy, then after the therapy so on, they wait, and then the image, the tumor, I see the image is a tumor shrinking, okay? And so that's, you monitor time. After a certain time, the treatment is over. But wouldn't it be nice that you are actually monitoring in real time, and that by various imaging modality is possible to monitor, because the same nanoparticle can put imaging modality as well as therapeutic. So all these three combined makes this very attractive for nanoparticle approach to work, okay? And we will expand that after 10 minutes break, okay? So how far what?
How far it has shown the result, isn't it? And it will be used now.
Well, all these effects are shown in some nano formulation. One nano formulation, can act much more efficiently this part. Another one can be this, another one can be. The challenge is the same nano formulation does all these combined, right? And so we will.
This food, who should do that?
Yeah.
That time monitoring technique.
Yeah, enhanced drug and imaging is easier. Controlled release
Yes, it
is
is.
a little bit more challenging. Okay, so we'll talk about it. Yeah,
From outside,
yeah,
to release the sample.
yeah.
And more thing,
Huh?
the two types of plasma membranes.
Yes, yeah.
As the diameter changes, then that will also shift.
Which one? What will also say?
The rod shape. So that is when you have a specific